In this lecture, I'll be discussing the two last topics of vibrational spectroscopy, but very important topics. That is the vibrational rotational spectra of polyatomic molecules and the effect of nuclear spin statistics on these spectra. So let's start with the vibrational rotational spectra of polyatomic molecules. Now, when we talk about polyatomic molecules, as we had seen in case of rotational molecules, because we are talking about the combination of rotation and vibration spectra, we know the selection rules for rotational transitions depend on the type of vibration that is occurring in the molecule. Let's say that means in terms of whether it's a perpendicular vibration or a parallel vibration. So we had seen this in case of rotational spectroscopy, that the selection rules for different types of vibration that is occurring, or let's say the selection rules for the different type of dipole moment changes that are occurring in a molecule defines what selection rules it's going to have, right? So now we'll see why vibrational rotational spectroscopy for polyatomic molecules is important, because those molecules which do not have a permanent dipole moment can still be determined using vibrational rotational spectroscopy, and their bond lengths can be determined. Okay, so when we talk about polyatomic molecules, we know we can characterize them into different types, the simplest of which is the linear molecule. So we'll start with that. Now let's say the linear molecule that we want to see looks something like this. Okay, now for this there can be a parallel and perpendicular vibration. Let's segregate that. Parallel vibration would mean that the vibration or you can say the dipole moment change that is occurring because of this vibration is along the principal axis. Now for this molecule, the principal axis is along this bond, which is C infinity. So that means the vibration that we want in parallel vibration is along this bond only. So this is the case of parallel vibration. And we had seen previously that for parallel vibration, the selection rule remains the same as it in case of diatomic molecules. Like this, you can consider to be just like a diatomic molecule, because in a diatomic molecule, you don't consider any kind of rotational change along the bond axis, right? So if that is true, we would get the selection rules to be delta V equals to plus minus 1. Concerning this is a SHO, but if it is not, it is an enharmonic oscillator. It can have all sorts of values. While delta J for both is plus minus 1. So that means just like a diatomic molecule. Now in that case, what value you will get for delta E? Delta E will simply be mu E 1 minus 2xe. Suppose I'm taking this only, not this actually, not simple harmonic, but enharmonic oscillator, but only the fundamental transition. And I will have plus minus 2bj plus 1 for delta J plus minus 1. Okay. So that means I will have P and R branch lines. No Q lines. Now this is exactly the same that we had seen in the last lecture in terms of diatomic molecules. Okay. Now, but if I take perpendicular vibration, now in perpendicular vibration, the change in the dipole moment due to this vibration is at any other direction, along any other direction, but not along the axis of or the principal axis. Let's say I'm considering the bending. Now suppose it bends in this direction. So the dipole moment, which was initially in this direction, has now gone in this direction. Let's say the same molecule on bending looks something like this. The majority dipole moment is still in this direction. You will have the resultant in this direction. That would mean it is no more along the principal axis, which was this initially. So that's why it's a perpendicular vibration. Now in case of perpendicular vibration, the selection rules for vibration is still the same. But for the rotational energy levels, now 0 becomes, delta G equals to 0 becomes an allowed selection rule or an allowed transition. Now we know delta G equals to 0 will give rise to Q lines. And that is why this is very important for linear polyatomic molecules. Why? So, okay, so for this one, the spectra should look something like this, right? This is the band center, or delta J equals to 0. There are no lines here. But if you compare it with this case, so this is your Q branch lines. This is your R, this is your P. So now you have these Q branched lines. Okay. So what you will get for delta E? Delta E will be mu E 1 minus 2xc plus for R it will be 2bj plus 1. For P it will be minus 2bj plus 1. For Q this entire thing will be 0. Or let's say what this means is, suppose you have two vibrational levels and these are the rotational levels. From the ground rotational level to the ground rotational level of the first excited vibrational state. This is your V equals to 0, V equals to 1. Let's say from first rotational level, or from the first excited rotational level of the ground vibration state to the first excited rotational level of the first excited state. There is no change in the rotational energy levels. Let's say this is J equals to 1, this is J dash equals to 1. Now, all of this is being done with the assumption of rigid rotor or approximation of rigid rotor. But we know that as it has moved to the higher energy level, the bond length is going to change for sure. And when the bond length is changing, we know the rotational constant is changing because moment of inertia is also changing. That means if I consider the non-rigid rotor approximation, then I will get B dashed and B, two different rotational constant. And for the same Q lines, the value or the formula for for the transition that I will get is okay. Now you can just simply consider the case. You can simply directly calculate this. Let's say for this you will get J into J plus 1, B dashed minus B into J plus 1. It's simply you're taking this part common and you get this. Now you know that B dashed is smaller than B, obviously, because R dashed is larger than R. So I dashed will be larger than I, hence this. Okay, so that would mean this is a negative quantity. That would mean you are going to see the lines on the lower frequency side of the band center. So if you have to determine where is the band center in this case, let's say after this there is the R branch lines. So this is your band center and you are going to see the Q branch lines on the lower frequency side, not on the high frequency side. Okay, now why is it important? Let's say for example CO2, you know, it has a bending mode which will bring both of them in this direction, which is in essential perpendicular vibration. Now perpendicular vibrations for polyatomic molecules, especially for triatomic molecules or linear molecules, is mostly the bending mode. Okay, not necessarily always, but mostly. So in this case, in rotational vibrational spectroscopy, for molecules like CO2 in perpendicular vibration, they will have Q lines, and from those Q lines you can find the rotational constant, and from rotational constant you can find the bond length. This will not be possible if it is a pure rotational spectroscopy, but it becomes possible in case of rotational vibrational spectroscopy. That is why combination spectra is very much important for determining properties of those molecules which are inactive in pure spectroscopy or pure rotational or pure vibrational spectroscopy. Okay, so this is all about linear molecules. Now we'll discuss symmetric top molecules, the second category of polyatomic molecules. Now let's take a look at symmetric top molecules. Now, when we were discussing rotational spectroscopy and we had discussed symmetric top molecules, now symmetric top molecules are those molecules which have two different moment of inertias. Let's say this is C, two equal moment of inertias along two axes and one different along the third axis, while the third one is not equals to 0, while it is 0 in case of linear molecules, but in symmetric top molecules that is not. You can consider an example to be CH3F, which looks something like this. It looks like a top, which an inverted top. Okay, so that's why the name symmetric top. Now, depending on whether this IA is smaller than IB or IA is greater than IB, you can have two different types of molecules, prolate and oblate. In this lecture, we'll not be going into that discussion. If you want to know about that, you can move on to the rotational spectra of symmetric top, that lecture. Okay, now if I want to write the energy of a particular energy level, for particular quantum level in case of rotational and vibrational spectra, I would get this to be EV plus ER. This is in accordance to Born-Polymer approximation. So this would mean this is mu E 1 minus 2xc plus bjj plus 1 plus a minus b k square. Now this k square comes in case of symmetric top molecules, spherical rotors and asymmetric molecules. Not asymmetric top molecules, okay. So this is actually the rotational change or the rotational transition that is occurring because of this different moment of inertia or along that axis. This B is the moment rotational constant coming from IC and IB, and this is coming from IA, which is the different one, which is the new moment of inertia which is present when you move from linear to symmetric top molecules. Okay. Okay, fine. If you understood that this is the rotational energy, this is the energy of the quantum level from which the transition is going to occur. For example, this is the one from where the transition is occurring. So again, depending on what type of vibration is occurring in the molecule, you can have parallel vibration and perpendicular vibration. Correct? So now parallel vibration, you will get delta V equals to plus minus 1, plus minus 2, etc. Now, one thing you should memorize is that there is no change in the selection rules for rotational level. That is, delta V is always going to be plus minus 1, plus minus 2, and so on. There is no change in that. The change that is occurring is in the rotational energy levels. Now, for delta J, you will have plus minus 1 and 0. And at the same time, delta K is 0. For parallel vibration, there is no change in the energy levels of K. Now, this K can have value minus the J to plus J. You can consider it to be like ML, which has values from minus L to plus L. Okay, fine. So if there is no change occurring in K, that would mean delta E is mu E 1 minus 2xc plus minus 2bj plus 1, and it will have all P, Q and R lines. Okay, now this is exactly the same that we had seen in case of linear molecules. So for parallel vibration for symmetric top molecules, the spectra is going to look exactly the same as you had seen in case of linear molecules. Now if you consider rigid order approximation, then that case, if you consider non-rigid order approximation, the same as in the linear molecules. Okay, fine. Okay, so this was concerning that it is non-rigid approximation. That is why we have a 0 here. Now, what's important here is that it is going to have Q lines, and it is, let's take the example of CH3I. It is going to have a strong Q branch. Okay, and let's say the intensity, the relative intensity of Q lines with respect to P and R is going to be directly proportional to the ratio IA by IB. I mean these two. So if IA tends to 0, that would mean there is no IA. That means the third so the third moment of inertia is gone. That means this is gone. We are only left with this two, and this becomes equals to 0. That means that is the case of linear molecules. So this changes to, then you will not have this strong Q branched lines. Okay, fine. Now let's say, for example, you're taking CH3I. In this, you will have very intense Q lines, and whose intensity is going to depend on this ratio. Okay, now let's take a look at parallel vibrations. We know for perpendicular vibrations. Okay, if I'm not wrong, this should not have been here, and this should not have, it will not have Q lines, or am I doing some mistake? Okay, no, this will be there. This will be there. Fine, everything's fine. So let's move on to perpendicular vibrations. Now, in perpendicular vibrations, delta V is still plus minus 1, plus minus 2. Delta J is plus minus 1 and 0. But now delta K is plus minus 1. Now, because delta K is plus minus 1, the formula for energy is going to change. How? You will get delta E. Let's say I am considering R branch. You will get mu E 1 minus 2xc plus 2bj plus 1 plus A minus B 1 plus minus k square, if I am not wrong, or I think it is 1 plus minus 2k. Okay, now, yeah, and if it is P branch, this simply is going to be minus, and if it is Q branch, this will be mu E 1 minus 2xc. This entire thing goes to 0. I have A minus B 1 plus minus 2k. Okay, now what you are going to realize here, what physical significance that is to be taken here, is that for each line in the R branch, there are multiple possibilities for the splitting due to Q lines, due to this K. Now K can have values from minus J to plus J, and for each of those values, you will have very different, many different types of transitions that are possible. That would mean, in earlier case, the spectra which look like this will now look something like this. So each of these will have many more transitions going on, even though their intensity will be very less, but the splitting is going to occur. And now because of these, it becomes difficult to resolve, because this A minus B vector, A minus B value is very small. And that is why these splitted peaks are very close. But in case, suppose you get that A is very greater than B, that means this has a considerable presence. In that case, you will get the peaks to be, even these small peaks to be little bit different, little bit splitted. Something like this. There you can find the rotational constant A. From there, you can get R and other properties of the molecule. So until unless you have the A, or let's say the moment of inertia IA to be very less, when A will be very high, till that time the spectra is going to be difficult to resolve in understandable terms. Okay. What else in symmetric top? I think that's all that I wanted to discuss about symmetric top molecules. We'll not be going into the discussion of spherical molecules in rotational vibration spectroscopy because no questions have come so far, and it's not likely that questions are going to come from it. And asymmetry is obviously difficult to even resolve in rotational spectra, so there's no question of that. We'll now move on to effect of nuclear spin statistics on vibrational rotational spectra. Before we start nuclear spin statistics, one thing that I wanted to mention about symmetric top molecules is that for molecules like CH3I, the intensity of the Q lines is dependent on the symmetry of the molecule. Now CH3I has a C3 or threefold axis. So in that case, the Q lines are, the intensity of the Q lines is strong, weak, weak, followed by strong, weak, weak. Now for symmetric top molecules, it is found that for every molecule, the intensity of the Q line depends on the symmetry. Like if you have a C2, it will be strong, weak, strong, weak. If it is C4, it will be like this. Now, I'm not going into the details of why this is happening, but yeah, you can remember this as a quick fact or a point while you go for the exam. Now let's take a look at the effect of nuclear spin statistics on vibrational rotational spectra. So at the beginning of the spectroscopy, we had seen that the wave function, total wave function, is a product of the wave function from individual modes of transition that are possible. Vibration, rotation, electronic, translation, and nuclear. Now we had removed nuclear and translation in our discussion on spectroscopy. Reason for nuclear is that we can discuss while we are talking about NMR, and for translation we don't have so far any kind of spectroscopic techniques in order to measure the transitions occurring between translation energy levels. They are so close. They are almost as close as 10 to the power minus 60 joules. Okay. But while we are considering rotational vibrational spectroscopy, nuclear spin statistics or the nuclear wave function has a very good effect on the type of spectra that is obtained, and we'll see now. So depending on whether the atom is a fermion or boson, we know total wave function is going to be anti-symmetric or symmetric with respect to exchange of particles. Now that particle can be an electron or an atom. Okay, so that means in principle this has to be anti-symmetric, this has to be symmetric. I'll be using A for anti-symmetric and S for symmetric. Okay, now vibrational wave function is always symmetric, translational wave function is also always symmetric. So what you're left with is that one more thing. Product of an anti-symmetric wave function with symmetric wave function is anti-symmetric. Anti-symmetric with an anti-symmetric is symmetric, and symmetric with a symmetric is symmetric. You can remember it in terms of minus into plus, minus into minus, and plus into plus. The product of signs. Okay, fine. So that means what all you are left with is psi electronic, psi rotation, and psi nuclear. Now psi electronic will be symmetric, and this you could know from the wave function. Let's say sigma g plus. For plus it is symmetric, for minus it is anti-symmetric. Now how to find the term symbol for polyatomic molecules is a part of different discussion. That is not part of this lecture. Okay, let us assume you know the molecular term symbol of a molecule in order to determine what is the effect of nuclear spin. So that means now let's say psi rotation. Now psi rotation, if it is symmetric or if it is antisymmetric. While it is symmetric, it will have only even J levels allowed. If it is antisymmetric, it will have only odd J levels allowed. Now, I'm not going to discuss here why it is symmetric and why it is antisymmetric. We are going to do in terms of a back calculation, like if we know this, this and this, we can find the rotational wave functions or whether it's symmetric or antisymmetric. While psi nuclear will be antisymmetric if I product 2i plus 1 gives the number of antisymmetric wave function, and it will be symmetric if I plus 1 product 2i plus 1 gives the number of symmetric wave function. While you are doing the questions, all you need to see is in which case you are getting a non-zero number. Now it will so happen that in one of the cases you are getting a non-zero number, and if in case you get two non-zero numbers, you will see in which one it is 1, because it needs to have either one antisymmetric wave function or one symmetric wave function. We'll see one example. So this is what, if you know what particle you have, you know it will be symmetric or antisymmetric. If you know what is the term symbol, you know it is antisymmetric or symmetric. If you know the nuclear spin of the atoms, then you can say it is symmetric or antisymmetric. Then it is easier to find this. Let's take the example of CO2. Each and every atom in this molecule has I equals to 0. Okay, fine. One more thing. Fermions have n plus half spin or half integral spin. They will have spin like this in integrals of half, while bosons have natural number spin or complete spins. This is their nuclear spin. In this case, oxygen and carbon both have nuclear spin 0. That means it is a case of boson. Okay, now if it is a case of boson, we know psi total has to be symmetric, and we know the term symbol in this case is this. That means the psi electronic is also symmetric. So what you are left with, we already have reduced it to this, so all we are left with is, okay, now we know this is symmetric, so that means this is, and symmetric multiplied by anything is going to remains the same. So let's say I'm removing this. I want to know what will be the nuclear spin symmetry. So I will have to see what is I. Let's say I'm starting with I plus 1 into 2i plus 1. This will give me 1. And if I consider I into 2i plus 1, this will give me 0. So in this case, I have one non-zero symmetric wave function. That means this is psi n is going to be symmetric. And if it is going to be symmetric, that means I am only left with psi rotation. That means for this to be symmetric, this also has to be symmetric. And if rotational wave function is symmetric, that would mean I only have even J values allowed. Now what does this mean that I have only even J values allowed? That would mean from, let's say 0, 1, 2, 3, 4, 5, transitions from even J values or even J energy levels are only allowed. That means transition will happen from here, from here, from here, not from these energy levels. That would mean earlier, if you were seeing spectra like this, let's say this is 0 to 1. Okay, I'm starting, let's say this is P branch. 0 to 1, 1 to 2. Sorry, my phone stopped recording because of low space. Okay, so in normal cases you will see a spectra like this, but because of this nuclear spins interaction, you will only see those peaks for transitions which are occurring from even J levels, not odd J levels. That means you will not see 1 to 2, 3 to 4, 5 to 6, and 7 to 8, and this spectra is going to look something like this. That means these peaks are not present. Now, what kind of question can come? In the normal spectra, you see that difference between two peaks is 2b, but in this case, it's going to be 4b because one peak is absent, so this 2b plus 2b, 4b. But the difference between the first P line and R line was still 4b and is still going to be 4b in both the case. Okay. Okay, so we have discussed CO2. Okay, fine. Now let's start with the questions that we have from this section. Okay, so the first question we have is from NET 2011, June. The question says the Q band in the vibrational spectrum of acetylene is observed. Now, acetylene is this, or let's say a linear molecule. That means Q lines will only be observed in perpendicular vibration, which will occur in its bending mode, which is given in your option number C. The next question is from December 14. If the component of the orbital angular momentum along the molecular axis of a heteronuclear diatomic molecule is non-zero, that means let's say you have HCl and along this is non-zero, let's say angular momentum. Okay, the rotational vibrational spectrum will show. Now it doesn't matter. Since it's a diatomic molecule, it is only going to have P and R branch. It cannot have Q branch because delta J is equals to plus minus 1 and not 0. Okay. Next question we have is from June 2017. Okay. The V equals to 0 to V equals to 1 vibration rotation spectrum of diatomic molecule, okay, exhibits transitions from R0, R1, P1, P0. Now, the lines are at 2241, 2254, 2216, 2203. Okay, fine. Now, what can you conclude about the molecule? Option D says is affected by nuclear spin statistics, but no, it is not affected by nuclear spin statistics because you are seeing rotational from both odd and even values. So rotation transitions, if possible, from both odd and even, that means there is no effect of nuclear spin statistics. The second is anharmonic vibration. Now you cannot make it out whether it's harmonic or anharmonic vibration. In both the cases, let's say it is only fundamental transition and delta V equals to plus minus 1 is both for harmonic and anharmonic. So that option is also not correct. Okay. Now the difference between these two values is 13 and here also it is 13. Let's say if I want to find the difference between these two values, not really. Have I made a mistake here? Yes, this is P1 and this is P2. So the difference between these two values, R0, P1, is 25. Okay. Now, if this is 13, you would expect one peak to be at 2229 and the difference between these to be 12. Okay, so almost okay. So how will you decide whether it is A or C. Now A has rigid rotation and harmonic vibration. Now as we cannot make it out whether it's anharmonic or harmonic, so we'll not go with this option. But option C says has rotation vibration spectrum, and the reason it has R and P lines is because it has rotation vibrational spectra, rotational vibration interaction. So that would mean this is option number C. The next question we have is from GATE 2007. Okay. The selection rules for appearance of P branch in the rotational vibrational absorption spectra. Now that absorption spectra would mean delta V equals to +1 and P will mean it is delta G equals to -1, which is given in your option number C. Okay. So I think that's all the questions that we had from this part of the vibration spectroscopy. Yeah, TIFR question we had already discussed. Okay, so with this we come to the end of the discussion of vibration spectroscopy in molecular spectra lecture series. In the next lecture, I'll be starting with the discussion on Raman spectroscopy and the classical explanation of Raman spectra. If you have any queries, if you have any doubts, please post them in the comments. I'll clear them in the comments or in the upcoming video.